We would like our robots to be more robust and reliable in unknown situations. For example, during an internal failure or an unexpected event in their environment. A good way to achieve this is by making our robots capable of self-adaptation. However, many current approaches to self-adaptation are highly application-specific, and thus usually require that you heavily redesign your control architecture. The Emros tool provides a reusable, off-the-shelf package for self-adaptation that can be integrated with any system that makes use of the widely adopted robot operating system. We will now go through a specific example for our robotic navigation application using the popular ROS navigation stack. Imagine we need to configure our robot to navigate safely while at the same time optimizing battery usage. To achieve this, we have different configurations, each of them with different quality properties. For example, a configuration with a low maximum velocity might be considered safer. Now, a ROS launch file should also be created to deploy each of our configurations. In these, you simply specify which nodes you would like to launch using which specific parameters. In the next step, we need to set up our application-specific ontology. We can use the Tomasis ontology already included in the Emros packages, and then we simply need to create the relevant individuals for our application, which can be done using the Protege tool. First, we create an individual for our function, in this case to navigate. Thus, I will call it fnavigate and assign it the type function. Then, we can create individuals for our quality attributes, safety and energy, and again, give them the appropriate type. Next, we can create an individual for one of our configurations, called a function design in this case, again giving it the appropriate type, while also indicating which function it solves through this object property. Now, while somewhat unintuitive, we also need to create individuals for the specific safety quality attribute estimation for this configuration, so that we can then link those to it. We then give these the type QA value, and also give them an object property to link them to the appropriate quality attribute types we created earlier. We also add a data property to indicate the actual number we desire. Now, we can go back to our configuration and link this individual to it through the appropriate object property. Finally, we will need to create an objective, link it to the appropriate function through an object property, and we also need to indicate the non-functional requirements related to this objective. We can then add any other configurations or quality attributes we might need. For the system to be able to monitor the quality attributes we have defined, we need to implement observers. Again, a lot of the provided code can be reused, and there are already classes such as Topic Observer and Service Observer, which should be used as the base for your specific quality attribute observer class. The most important part here, in the case of a Topic Observer, is to define which topics you want to listen to, and then, in the Calculate Attribute method, define any calculations you might want to do with the data contained in these topics to calculate your quality attribute. Finally, we need to configure our metacontroller through a configuration YAML file. The most important part here is to list all the available configurations and specify their respective ROS launch files, created in an earlier step. It is also necessary to specify which nodes need to be killed for reconfigurations, as well as what actions and goals might need to be saved between each reconfiguration. Now we can proceed to run the system. In this recorded simulation, you can see our previously described example of a robot navigating a factory floor and trying to do so in a safe and energy efficient manner. An animation of the recorded data for the energy quality attribute measured by our observer is also included. Now, we can see that once the quality attribute goes above the threshold of 0.6 set by the objective, a potential reconfiguration is triggered. Emros will use the ontology we defined and an off-the-shelf reasoner to try and find a better configuration. In this case, for example, a configuration with a lower energy QA estimation is chosen.